Hi everyone, and welcome to our second lecture video going to be exploring the concept of partial pressures, which is still based off of our ideal gas law conversation, which is still part of Unit 3.4. So the cool thing about pressures is that pressures are additive, meaning if I want to know the total pressure in a system, and I know the individual pressures of each of the gases in my system, I can just add them up, and that would be my new total pressure in my system. So here in this example, we have three gases. We have this blue gas here, this purple gas, and this yellow gas. And if I combine all of these together to make this mixture of gases, we can go ahead and add all of their individual pressures to equal my total pressure. So I take 300 plus 600 plus 450, which are my individual pressures. Notice the units here are kilopascals, and that's a unit of pressure. When I add all of those together, that equals the total pressure in my system. So if I know the individual pressures, this is a super handy way to find the total pressure, but sometimes I might not know the individual pressure of my gas, and maybe that's what I'm interested in exploring more. So we can start to connect this new concept of mole fraction to our conceptual understanding of partial pressure. The mole fraction of a mixture can be utilized to determine the partial pressures from the total pressure. Something that I want to emphasize, an idea of a mole fraction. If we think of a fraction, we have a part over a whole. So a mole fraction is the moles of my individual gas divided by my total moles of gas in the system. And we'll see that again in just a moment. So the mole fraction, the variable for mole fraction is capital X that equals the moles of a component divided by the total moles in our system. So if I have a mixture, and in my mixture of gases, I'm mixing gas A and gas B together, and I want to find the individual partial pressure of gas A and the individual partial pressure of gas B, and I know how many moles of each we have, we first want to solve for our mole fraction. So the mole fraction of A is my moles of A divided by my total moles in the system. In this case, it's moles of A plus moles of B. And then our second option would be if I want to find my mole fraction of B, we have our mole fraction of B equal to the moles of B, because that's what I'm interested in, divided by the total moles in our system, moles A plus moles B. And let's say I know the total pressure in the system, meaning I know the pressure of A and B combined. What I can do now to solve for the individual partial pressures of A and the individual partial pressure of B is I take the total pressure, P total, and if I multiply that by my mole fraction of A, that gets me my partial pressure of A. And let's notice our notation here. P subscript total is my total pressure. If I multiply that by my mole fraction subscript A, so that's my mole fraction of A, that gets me my individual partial pressure of A. So that's the individual pressure of gas A. If I wanted to find my partial pressure of gas B, I would take the total pressure here and multiply that by the mole fraction of B to get my individual pressure of just gas B. So if I know my individual moles, I can figure it out this way. But in a practice problem I'm about to talk through, we can also just utilize the ideal gas law as well. So let's talk through an example. Here in this problem, we're told a 10-liter vessel contains 2.5 times 10 to the negative 3 moles of H2, 1.0 times 10 to the negative 3 moles of He, and 3 times 10 to the negative 4 moles of Ne at 35 degrees Celsius. And it's asking us, what is the partial pressure of each of the gases? Notice, I'm not given a total pressure here, right? Which means I can't use the approach we just introduced because I would need to know the total pressure. So when I think back, if I want to solve for the individual pressure of my gases, I can end up using my ideal gas law. Here, I'm interested in solving for the individual pressures, so individual pressures, P, for all of my gases. So if I want to solve for the pressure of just hydrogen gas, I would plug in just the number of moles of hydrogen gas. If I plugged in the total moles here, that would get me my total volume, which might be helpful, but I'm more so interested in just the pressure of H2 because that's what the question is asking. So let's take the easier way to do this. If I plug in just my number of moles of H2, I plug in the ideal gas constant, the temperature and volume of our container. Notice it might be funky here. If I'm looking at just one gas and not the total gas, why am I plugging in the total volume? The reason I plug in the total volume is because gases occupy the shape and volume of their container. So hydrogen gas has a volume of 10 liters, so does helium, and so does neon, even though it's a mixture. The reason is because each of these gases occupy the same volume and shape as their container. So when I plug in all of these numbers, I get this individual 6.32 times 10 to the negative 3 atmospheres. What this means, that is the pressure of just hydrogen gas in my system. I can then do the exact same thing for helium and neon, except I want to plug in those specific mole amounts. So for helium, I would plug in the number of moles of helium. And for neon, I would plug in the number of moles of neon. And I would get different pressures because there's different quantities of each of these gases. So my partial pressure of helium, P subscript He, is 2.5 times 10 to the negative 3 atmospheres, and the partial pressure of neon is 7.58 times 10 to the negative 4 atmospheres. So I have my individual partial pressures for each of my gases. Now for part B, it's asking what is the total pressure in atmospheres? And for me to figure out the total pressure, I need to sum all of the partial pressures. So I take my partial pressure of H2 and add that to my partial pressure of helium and add that to my partial pressure of neon, and I end up getting my total pressure, which is 9.61 times 10 to the 3rd atmospheres. So with that, that's the last lecture video. And now I would challenge you to work on your gas laws worksheet for the rest of the hour allotted. Bye, everyone.